Okay, so we're talking about nitrogen and potassium now in mature orchards, and we're gonna do a 1-2 punch here of academic nerd and a practical person, me and Devin Clarke from Yara, I'll talk about the research behind how we know how much nitrogen and potassium is necessary for mature almonds and in what time, and then Devin's gonna clean up the mess that I make. So thanks in advance, Devin, wherever you went. No pressure. All right, so almond nutrient management, particularly nitrogen and potassium in mature orchards. I'm gonna be making reference a lot to this BMP booklet, I guess we can call it, that the Almond Board has created out of a lot of UC research, that much of which they co-funded. You can get this in the back, among other places. You can get it online. And I know they're going to be doing a reprint of it pretty soon also. And their graphics are a lot better than my PowerPoint graphics. So when we're talking about nutrient management, especially nitrogen, the first place we can start thinking about this is a matter of supply and demand. And we still talk about balancing a checkbook, even though that's getting less and less relevant to newer PCA audiences who are like, what's a checkbook? But guessing, not to judge too much, most of the people in this audience have met a checkbook before. So we're trying to think about balancing the needs of the tree for nitrogen and the supply of nitrogen that we're putting in, because for a number of reasons, right? We know that if those two are disjointed, if we don't have enough supply, then the tree is going to be deficient. If we have too much supply, then the nitrogen can leach out of the root zone and into the groundwater, which we don't like for environmental reasons. That's groundwater that our neighbors are also drinking. That's groundwater that's being regulated. And that's nitrogen that we paid for that's not going where we asked it to. So you can see here the sort of components of nitrogen demand over the course of the growing season, getting up into the tree. So through the course of bloom, leaf out, fruit development, and leaf drop, nutrients are needed, nitrogen is needed. And there's various components of this supply that we can think about. We think automatically about the synthetic fertilizer that we're putting in, but we need to also consider that there are other components that could be meeting this demand. Compost, composted manure, the nitrogen that's in our irrigation water, cover crops, etc. So we're trying to keep these two things in sync as much as possible to minimize what goes out of the root zone. And as we do that, we can think about two components to making that magic work: soil dynamics and root uptake dynamics. So when we think about soil dynamics, it's helpful to know, right, that we have a lot of different forms of fertilizer that we could be applying, and they have different dynamics in the soil. So we can think about organic nitrogen, like compost or composted manure. We can think about urea, ammonium, and nitrate. When it comes to a leaching perspective, it's important to know that all of these things can turn into nitrate eventually in the soil through bacteria and microbes that munch on them and process them in the soil. And so no matter what form of nitrogen we put on, it can eventually turn into nitrate, which is then susceptible to leaching out of the root zone where we no longer can really access it. To get from ammonium to nitrate, that happens in California soils in a matter of days to weeks. I think it's 2 weeks, about 40 to 50% of ammonium can turn into nitrate in midsummer soil conditions. Urea just takes a matter of days to turn into ammonium, and organic nitrogen can, from a matter of weeks to months, turn into ammonium. Now, just to sort of illustrate this point a little differently, this is a figure from the IPNI, the International Fertilizer Institute, more or less. So we can see here there are different soil types going from left to right, and from top to bottom, different sources of nitrogen. To just sort of hammer home this point in a different graphic way, so what you see, this is, they put on these different forms of nitrogen, and then they irrigated them in for half an hour, and then they took these incremental soil cores to see at what depths they could find that nitrogen still. And so what I want to hammer home is that you see with all the ammonium sources, regardless of soil type, most of that ammonium is still in the top of the soil, the top 3 inches or so. Urea moves very quickly through the soil. So we see that that's all gotten to a deeper depth after 90 minutes of irrigating. but that by far the nitrate moves fastest through the soil. So after just 90 minutes of irrigating, they found the majority of that nitrate is already at 9 inches. So that's soil dynamics. So just keeping in mind that any nitrogen that you apply can eventually turn into nitrate. We know nitrate moves quickly through the soil with water. Another thing to keep in mind is the dynamics of uptake through the roots. And this is influential because uptake is regulated through these either channels or transporters that get nitrogen into the roots. All right, so if we see this blue lightning bolt as sort of our generalized root for this tree, and when you see that like flash kapow yellow there, that means energy is being used. All right, so ammonium can get into the root without using energy, but the tree needs to turn it into amino acids to keep it safe. Otherwise, it can kind of wreak havoc in the system of the root. And nitrate the trees use energy to take up nitrate. So trees are going to regulate this uptake because it takes energy to do it, right? They're not going to take it up just because it's around. Another way to think about this is looking at nitrate in particular. So the uptake of nitrogen as we go up that graph, concentration of nitrogen that's in the solution as we go across that graph. There's different transporters in the roots that might take up nitrate, but what we see is that's the nitrate concentration at a typical fertigation event is way out on the end of that plateau. So the more nitrate we apply, the more nitrogen we apply, diminishing returns there in terms of uptake. This is another way to illustrate this. This is from research that was done in Patrick Brown's lab. And they did different rates of nitrogen at one big orchard project in Kern County. So you can see the red is the lowest rate of nitrogen, well below what the trees needed. As we get into green, going up there, that's more meeting the tree needs. We get to blue, that's definitely meeting the tree needs. We get to the dark green, that is well beyond what the tree needed. So you can see, and this is the leaf concentration as a way to measure is the tree taking it up or not. From the insufficient, add 75 pounds to get to that bright green, there's a big response in uptake. We get a little more nitrogen, there's a more response in uptake. But then when we get to adding another 75 pounds to get from 275 to 350, almost no response in uptake by the tree, right? So this concept of diminishing returns as you're applying more nitrogen. So we put these things together using this system of the 4 R's, which is, we're nerds, we're not marketing people, so 4 R's is kind of a cheat because we just put the word rate in front of everything. But right rate, right time, right place, right source. You guys are living in this post-irrigated lands regulatory program world. You've probably heard these 4 R's before. But the right rate, we're talking about matching, in the big picture, matching that supply to the demand. Right time is sort of zooming in on that picture more, so matching the application timing to the timing of that demand. Right place is thinking about that leaching out of the root zone, making sure that we're getting the nitrogen to where the tree can actually take it up. And right source is keeping in mind those different patterns of behavior of fertilizer and what will match your particular orchard for the vulnerabilities of leaching in your orchard, your irrigation system, et cetera, to minimize that leaching, maximize that uptake. Okay, so how do we know right rate? And really, Patrick Brown should be giving this talk because it was his lab that did all of this. But I'm stealing some of the glory and letting him put his feet up a little bit because he has a talk to do later also. Yeah, I see he actively puts his feet up. Right rate was this enormous multi-year, multi-site project that they did to figure this out with funding from the board and a lot of collaboration from growers. When we talk about right rate, because we're in perennial crops, man, like the lettuce guys, the tomato guys, they have this stuff so easy in terms of research because you just grab the plant and yank it out and dry it and throw it in a grinder at different stages throughout the year, and then you're done with the plant at the end of the year. But we have to think about not only growing the crop, but growing the tree as well, right? So when we think about the rate, the demand, we're thinking about what's going into the crop, but also what's going into growing the tree. So they found that there's 68 pounds of nitrogen in every 1,000 pounds that goes into making every 1,000 pounds of nuts, all right? So that's more than just what's in the kernel, but that's also what goes into making the shells and the hulls that you're pulling off of the orchard. There's another 40 pounds of nitrogen per acre dedicated to tree growth in the age range of 6 to 15. As you're younger than that, you're putting on a lot more growth. As you're older than that, trees are really filled in. There's not as much incremental growth every year. So some quick math around this. If you've got 2,500 pound kernel pound crop expected, you would then multiply that by 0.068, or just 68 over 1,000, and then you add 40 pounds on top of that. So if that's 2,500 pounds per acre expected, that's how you get your nitrogen demand. And if you don't like doing math and just want to go off a table, there's a table in this handy-dandy booklet for you to refer to, and that also talks about the demand at younger and older tree ages. Backing up to that figure, that nice figure that had the trees and all the things, all the supplies going in, we do need to keep in mind that 110 pounds is what's being demanded by the growing crop and the tree. That's not necessarily what you apply, all right? So when we think about the right rate of what we're applying, we need to keep in mind there's stuff we're already applying that's not our synthetic fertilizer. So we're probably putting on nitrate in our irrigation water, right? Most of us have nitrate in the irrigation water. If you're using groundwater, that's why we're in this regulatory quagmire in the first place. That's free nitrogen, right? Especially in these lean years. Don't forget about that. The regulators won't let you forget about it anyway. This table is also in that chart. So if we think we're applying 3 acre-feet of water every year, 36 acre inches, and we've got 10 ppm of nitrate, that's already supplying 18 pounds of nitrogen. We see that on the top table there, kind of in the middle, 18.3 pounds, right? And keeping in mind that the figure you get back from your lab, if you're sending your water to a lab, might tell you nitrate, or it might tell you nitrate nitrogen. These are slightly different numbers. All right, so that's our right rate, our 68 pounds for every 1,000 kernel pounds and 40 pounds per acre for tree growth. Now let's get into right time. This table, I'll say, or this chart, though lovely, is getting revised in the next version of this that goes out, because there was a little miscommunication between the scientists and the graphic artists. But the table is very accurate. So what you see in large here is my revision of that chart. So what we know is that the nitrogen that goes into the crop and that's taken up by the tree increases over the growing season. That there's a huge, almost linear increase in the need for the crop. So by the time we get to 100% hull growth, so the fruit is entirely sized up, which is usually around mid-April, depending on the year and the variety, but let's say normal year, nonpareil, 30% of the uptake has already happened for nitrogen. By the time we get to kernel fill, which is usually around mid-May, again, generically speaking for nonpareil, 55%. By the time we get to all the weight being accumulated in the crop and just starting hull split, like it's smirking at your joke, but it's not like open mouth laughing at your joke. I'm alone in orchards a lot telling jokes to almond trees. We're at 85%. That's the vast majority of our nitrogen's been accumulated by then. This is maybe a more accurate way to look at it, though not as visually pleasing, from scientific literature. So again, about 30, about 55, and about 85. What I know Devin is going to refer to here, but I think it's a point so nice we can make it twice, is that then applying this to your actual production practices is a little more complicated. Because, all right, so let's say we apply 30% of our nitrogen by that 100% whole growth timing, right? By what we see there on that first red dot going up the slope. If you just apply 30% by then, and you're not applying any more until that 55% need timing I told you about, well, there's that whole white space of, the green arc is the demand of the tree, And the filled in underneath in the blocks is what you're applying. So there's that white space where the demand is not being met by what you apply. And you can see, those little white spaces as we go up. And then shortly before harvest, we're probably over applying because we're not going to be able to get in there to fertigate because we're drying the ground down, et cetera, et cetera. You could go the opposite and you could say, okay, I'm going to put on my first fertigation when the soil is dry enough, I think, to take it up, especially in the San Joaquin. It's a little different where I'm from, up in the North State. And I'll say, okay, in mid-March, I'm going to be targeting that mid-May demand. Well, then we have the opposite problem, that you're applying a lot more than the tree needs or the tree can take up in that time. You can kind of split the difference. We're lucky enough to work in a perennial system where there is some buffering of nitrogen in the tree itself, in the perennial tissue. But I think the even better approach is, instead of 4 fertilizer applications, splitting that up into as much spoon feeding as you possibly can. And I know that Devin's going to talk more about that. All right, so we've got our right rate, 68 pounds for every 1,000 pounds, plus 40 pounds for tree growth. We've got our right time, thinking about that, this progression of demand over the growing season. Now let's talk about right place. So right place is really actually as much, if not more, about thinking about where your water goes, because that nitrate is so vulnerable to leaching. And managing both where you put your nitrogen and where your water goes depth-wise because of where the roots are, right? Roots take up nitrogen. And a lot of people have been removing orchards lately, so you probably have a sense of the root depth. Certainly you can find some roots down to 2 feet, 3 feet, 4 feet. Astrid Volder, who's our root biologist at UC Davis, would tell you can find them even down to 6, 7, 8 feet. Those are mostly going for some big, deep water. What we're thinking about is not just where you can find some roots, but where the majority of the roots are, right? Because we don't want to just rely on one root goalie that's stuck there at 4 feet to maybe catch that nitrogen as it goes by, right? We want to be keeping our nitrogen where the majority of the roots are. And again, work out of Patrick Brown's lab. They use these cool cameras and these clear tubes to look at where you can find roots at different depths. So they took these pictures at different incremental depths going down in the root zone. And I mean, man, I don't know if any of you have gotten your undergrad and you're like, maybe I should go back for a master's or a PhD. This guy just had to sit at a computer and count roots for 3 years. So God bless Andres Olivos for doing this work. I hope he had a good podcast. So we can see there, and these are different fertilization treatments. What the bars are doesn't matter nearly as much as the fact that whether you're blue or red, there's far fewer roots once you get below about 1.5 feet, right? So 16 to 20 inches, things really start to diminish. You don't have nearly as many goalies there to be able to grab and catch that nitrogen. It's probably going to fly by. So not only are you applying, laterally, horizontally, your fertilizer where the web of roots going out is, but we're thinking about that depth. We're thinking about, as we irrigate, trying to keep our water mostly in that zone because that's where the nitrate is going to be. Okay, right source. I don't want any spoilers for Devin's presentation, so I'll let him go into that. I'm going to add the 5th stepchild R of this whole thing is right leaf sampling, which, as we're tightening our nitrogen belt, because it's leaner times for prices and it's getting more and more regulated, this is a way to kind of keep tabs on what's going on in your tree, how the tree is reacting to less nitrogen or a changing pattern of nitrogen application. Certainly, at least relying on July leaf samples. You can also take April leaf samples to predict what your nitrogen content in your leaves will probably be by midsummer, but certainly at least annually checking your leaf nitrogen levels in July. This little booklet goes into how to do that, but we want to be sampling between 18 and 28 trees, 30 yards apart. sampling 5 to 8 non-fruiting spurs from each of those trees. If you're fairly confident in the uniformity of your orchard, you can go more towards fewer trees. If you have a more heterogeneous orchard, more trees, I would say, to kind of grasp the whole situation of that orchard. Send it to a lab, etc. So if you're in that range of 2.4 to 2.8, congratulations, that's where we want to be. If you're on that lower range, I would just, definitely keep an eye on that, because that might mean if you're in a varied orchard that's not homogeneous, some of your trees are getting less, some of your trees are hitting under that metric, and some are hitting higher, because that's an average, right, of your whole orchard. If you're less than 2.4, it's worth rechecking your supply and demand calculations. Certainly this can be difficult, because we're projecting what you think the crop will be, and you're applying based on that. Maybe bloom was better than you really appreciated, maybe your set was higher, and the demand was higher. If you're under that, also reconsidering your timing of application. That it might be that overall you're putting on enough, but some of it is leaching through because you're putting in slugs that are too big, slugs that are too late past the timing of demand. Considering your irrigation strategy also. And I would add to that, considering your distribution uniformity, because most of us are putting on our fertilizer in our irrigation system now. If your irrigation system is not very uniform, through clogged emitters, through just age of the system, you might be putting on more nitrogen in some trees and less in other trees in the same irrigation set than you theoretically think you are. Or you might be putting on more water in a non-fertigation set and flushing some out of the root zone for some trees. I know that the CDFA and a number of funding sources have put in a lot of money into helping growers do distribution uniformity testing. So a lot of RCDs now have mobile irrigation labs. I know the Almond board is funding some of them to do that and is also doing their own DU testing. So I would say if your orchard is over 8 years old and you haven't had a distribution uniformity test, call the Almond board, call Tom, and talk about your options. And if you're over 8.2, well, then something's also out of whack, or I should say, not out of whack, that's too critical, but there's room for improvement. So certainly looking at what you're supplying, are you counting everything? Are you counting the nitrogen that's coming from your water, from compost, et cetera? And can we hone in on a better demand estimation? And more than anything, I'd say keeping track of the interannual, across years trends of these as you are changing your nitrogen management practices in this new regulatory era to see how your trees are responding to those changes in management. Okay, so then potassium is a much shorter presentation. Similarly, we're getting potassium not just for growing the crop, but for also growing the tree. But really, especially the hull is the key demand part of that potassium. So same experiment, they looked at the potassium in growing the tree and the crop, and it found 80 pounds of potassium is needed for every 1,000 kernel pounds that you remove. Your estimated crop per acre times 0.08 gets you to your potassium demand. The curve, the timing of demand is quite similar to nitrogen. So I would say you can pretty much go according to the same curve. And similarly to nitrogen uptake dynamics, potassium takes energy to take up and to process by the tree. So you reach a point of diminishing returns. Putting on more potassium than you need is not going to necessarily be taken up by the tree. And given the price of potassium, I don't think anyone wants to put on more than they need. We sort of have the flip problem with potassium that we have with nitrogen, not that it's super susceptible to leaching, but actually that it's can very easily get tied up in most of our California Central Valley soils. But even though it's the opposite problem, we find a very similar solution. If you can be putting this on in a spoon feeding approach, which the Brown Lab found, continuous fertigation led to higher leaf potassium levels than 4 slugs of potassium in 1 year. And it's because you're kind of keeping that potassium in solution if you're spoon feeding it, so it can be taken up by the tree. Then when we talk about that, kind of feeds into right place also, old school wise, We were doing our 2 big banded strips of potassium in the fall, letting the winter rain move that in. We've gotten more into putting it on through the drip emitters or spreading it in the tree row where our micro sprinklers are going to continue to wet it in because of this problem. If you're putting on your banded strip outside of the wetting zone, there's just a lot of the year that potassium's not going to be in solution in a way that the tree can take it up.
Yeah, Katherine, you mentioned the 40 pounds of N for vegetative growth when the trees are in years 6 to 15. And I know in the past we've been told that 40 pounds was built into the 68 units of N formula once you exceeded 2,000 pounds. So are you now telling us to add that back in? And then the second question is what about our efficiency of application? Are we no longer going to divide by efficiency factor to calculate our total nitrogen?
Yeah.
Those are the 2 questions.
Okay, great question. And thank you for bringing that up. It's great to have very sharp people in the audience. And yeah, I think where did we land on that amount when to build it in? Yeah, Patrick can answer that maybe.
You can answer.
All right, I'll step in and save your butt here.
Great.
No, you're absolutely right. We did move from the assumption that the 68 pounds contains sufficient nitrogen for all of the vegetative growth into breaking it out. And that was a consequence of listening to growers who had difficulty with that general concept of thinking about, I've got a big vigorous tree, young tree versus an old tree. So part of it was to make it a more amenable system, more understandable system. The second part of your question is to taking out the inefficiency. That sort of came from discussions with Irrigated Lands Regulatory Program and the concept that building in inefficiency, assuming inefficiency, was an equally bad message to be sharing. So the combination of both adding an explicit vegetative nitrogen demand, potassium demand into the equation, and offsetting that by not admitting that we can do a 75% or 80% efficiency is sort of the collaboration and the solution that we came with. We're very confident that those are excellent ways to think about it. One of the things to often don't say this out loud, but if you're putting on 280 pounds of nitrogen because you got 4,500 pounds of nuts, choosing an 80% efficiency value will leave 64 pounds of nitrogen in the soil, which would be out of compliance with Irrigated Lands Regulatory Program. So emphasizing that we always must be as close as possible to efficiency is really the best way to go.
When you're calculating your N applied, I would not depend on getting 100% NUE, but I don't want to say a particular projection of your nitrogen use efficiency that you should be targeting, because that is changing so rapidly, and as Patrick said, that's just not something we can say out loud in this regulatory environment.
When you're talking about your calculated in efficiencies, when it's applied and when it's released, how do you do those efficiencies with compost? Because as we're irrigating during the summer, as the soil heats up, it's releasing more nitrogen.
Yeah.
How do we take that into consideration when we're trying to figure out our N applied early in the season?
So calculating nitrogen release from compost is its own half-hour presentation. I would say it because it depends on the timing of when you're applying that compost. If you put it on in the fall, there's a huge slug of release that comes pretty shortly after that application. And yeah, I don't have a solid answer for you. So if it's mature compost, I would anticipate something like 20% of it gets released over the growing season in a fairly drip, it's dripping out slowly as you're irrigating it, as you say, as things are getting warmer and the microbes are processing it. From one slug of compost, you'll get a lot of that at the initial, well, depends on how much it's been matured, but that would be my rough, so 20 to 30% in the first year of application, and you're getting maybe in the 5% realm from previous years of application. So it depends on how long you've been applying it. That's my off the top of the head. We can talk after a little bit. And I know there's some links to compost nitrogen availability calculations that are also in the booklet.
So my question is,
Thank you.
we've gone through the 68 pounds per thousand
Yeah.
with added nitrogen, without, and the efficiency factor. So am I assuming that as long as I get there at harvest at 2.5, 2.6, I've done a good job? Is that a reasonable assumption?
Well, if you're at 2.5, 2.6, you've done a good job meeting the demand of your trees.
Okay, that's the important part, I think.
Depends on who you're asking, right? Yes, as a production agriculture room, that is the important part. Down the line, depending on how out of sync, so I could use step to the side one way or the other, out of sync your application is with what you removed or was removed into the growing tree, that might not meet what the regulators are comfortable with. Yeah. So that's a real, yeah. So there's the production, yes, that if you're in that zone, you're good production-wise. Are you good in that zone forever regulatory-wise? That's different.
Okay, so I know there are more questions. During the break, maybe you can follow up with
Sure.
Katherine. I would like to invite Devin up to the stage. And in the meantime, Eric had a quick comment about efficiency.
Yeah, just wanted to touch on that nitrogen use efficiency question. And some of this may be due to, some differences in how different regions are kind of accounting for nitrogen and different expectations. But as far as the Central Valley Water Board goes, and unless there's been some conversations maybe I haven't been privy to, we don't have any expectations as far as an assumed nitrogen use efficiency or not assuming, the reality is that it's not going to be perfectly efficient. So, off the top of my head, that could actually cause some issues with potentially under-fertilizing, which is not producing, a healthy crop, which is ultimately going to affect yield, which is ultimately also affecting how much nitrogen is being uptaken. But I guess at the end of the day, what I want to emphasize is even if you are assuming some sort of inefficiency, that's really the preseason budgeting. You should be adjusting throughout the season to whatever your anticipated needs are. So, for first blush, that's fine. As you get better information, you should be adjusting your fertilization quantities. So just want to throw that out there.
Thank you, Eric. And now we move to Devin.
Wonderful. Thank you. Well, I think by looking at your agenda, you can see who the odd man out here is. And so I appreciate ABC allowing me to come and talk to you all about commercial nitrogen and potassium sources. And we are going to have to kind of approach this from a generalized standpoint, but we're going to be looking at some management implications relative to different sources that are available. So as Katherine hammered, and I would be remiss not to touch on in any presentation about nutrient stewardship, is the 4 R's. And so here we're going to be talking about right rates, right time, right place, and right source, more importantly, though. And here you see that you have NP and K captured there as the right source, but there are even nuances of different nitrogen forms and different potassium forms, as well as phosphorus, that we need to be considering in our programs. So the first fundamental thing for me as both an advisor and also working in the crop fertility space is that we create a definitive budget going into any cropping season. And so we have a yield target in mind based off of historical yield trends, as well as where we see our bud sets and any observations that we're making in the field. So the critical pieces here are, one, understanding what is going to be our total nutrient demand for the entire growing season. We want to be able to try to qualify what this total demand is based off of that yield target and our efficiency or our historical reference of efficiency for different nutrients. And we do want to be able to break this down by all the different nutrients that we're going to be working into our program. And then beyond just looking at those seasonal totals, we want to be able to understand how is that nutrient going to be partitioned throughout the growing season relative to that demand curve that we saw previously for nitrogen. But the Belridge project itself actually produced graphs for every single nutrient from nitrogen down to boron. And so those are important to be able to follow and use as guides. So I did capture here, you'll note that this is P2O5 and K2O, so the oxide forms, potassium and phosphorus, and those are critical to understand, and we'll actually address that in a later slide. So once we have kind of created a budget to work off of, and as the gentleman here from the Water Board mentioned also, we want to be continuously updating these and referring back to our program throughout the growing season to make sure that we are making corrections where needed. But we want to go now to looking at the different product classes that we have available to us to be able to meet the demands that we've already identified. And so we're going to break this down to kind of commonly fertigated inputs versus commonly broadcasted inputs. And I say that because some of the products that exist on some of these graphs that I'll be putting up here will actually be commercially available in a liquid form or be available in a dry form as well. So on our commonly fertigated inputs, these are ones that we're running through our irrigation systems. A lot of cases we'll see these are going to be liquid, but sometimes we might see soluble products that are going into liquid solutions. These are going to be blends or straight line products, so single nutrients or multi-nutrients in most cases. True solutions or suspensions. The suspension representation may be like a solutionized SOP. We'll see a lot of lower analyses compared to some of our dry products in a lot of cases, and utilizing these for in-season management. And there's a degree of plant availability that usually comes along with a lot of these fertigated options. On the other side, we have our commonly broadcasted materials. These will be dry in a lot of cases. Again, these can come and exist as blends or straight line products. We'll typically see higher analyses achieved with these types of inputs. And in a lot of cases, we will use these on the peripheries of the management season itself. So either leading up to that 70% leaf out mark or that early season time period, or we'll use them post-harvest historically, be trying to rectify some of the shortcomings in our program from the year prior and loading up the soil or trying to get those trees prepared for the next year. And because of this, we often see problems with nitrate leaching on the side of nitrogen inputs being broadcasted dry, as well as potassium fixation. So now that we have kind of a rough understanding of our budget and some of the different classes of fertilizers out there, it's important to build a resource for yourself as a grower or as an advisor as to those different sources that exist in the industry, and being able to use a form like this to be able to put in different rates of these different products that you may be considering for a particular program, and understand how that's going to help you reach those demand objectives that you have already identified for your particular crop. Note again here, this is where it comes again that phosphate and potash are utilized, the oxide forms. And this is because when we get our analyses back or our recommendations from a soil lab in most cases, that recommendation is going to be coming with the elemental form of potassium and the elemental form of phosphorus. And so we need to recognize that both phosphorus and potassium on a fertilizer label are expressed in their oxide form. And there are vast differences between that elemental value and that oxide value. So as an example here, potassium is the one that's not as significant, but phosphorus, there is a big difference between that oxide and that elemental value. So if we were going to look at a calculation to figure out how to transform that recommendation value in the elemental form to a fertilizer label value, we'll take that elemental K value and divide that by 0.8301 technically, but you can round that. And that will give us what our K2O needs are. Okay, so if we do an example and we say that our lab report comes back, says we need 100 pounds of elemental K, then we need to divide that by that 0.831, and that tells us that we need 120 pounds of K2O fertilizer inputs, right? And so now that we have that 120 pounds of that fertility input that we require, we can take that to an individual product using triple 15 in this case, and divide that by the percent analysis of the potash in that product. So that's the 0.15. So that 120 pounds divided by 0.15 is going to tell us we need 800 pounds of this particular product to supply our elemental K needs that have been identified. So it's not a great way to describe it, but primary and secondary terms have very specific definitions in terms of mineral fertilizers. And so when I talk about this oxide form and also some other input products that we utilize, I will highlight those later. But there are some baggage elements, we'll call them, that come along with some of our specific nutrients, our targeted nutrients that we're focusing to work into our program. And so that's really important to be aware of, and there's multiple reasons for that we'll cover. But sulfate in the form of potassium sulfate or potash, sulfate of potash comes along with it. If we have K-mag, you have magnesium that comes along with it, as well as sulfate. And then our MLPs come along with chloride. So important to be aware of what's coming along with our products. And this is a great representation of being aware of what those baggage elements are coming along with our inputs. So if we're looking at maybe a representative early season program for a lighter textured soil where you're going out with ammonium sulfate at 200 pounds and 400 pounds of SOP to try to supply those potassium needs, right? You have to be aware that you're carrying along 116 pounds of actual sulfur with that single application, even though you're focused on that nitrogen and that potassium only. And for reference, a 2,500 pound crop only needs about 8 pounds of actual sulfur. So you've overshot that and then some, right? And the ultimate fate of that sulfur that's coming along with those two products is that in the early season, you're likely going to leach that all out of the root zone. It's not going to be available to the crop. You're not going to be able to balance that against those nitrogen sulfur ratios that are required. And if you have anything like free calcium out there, you're ultimately going to make gypsum and lock up both of those mineral nutrients at that point in time. So it's just important to be aware of what are we carrying along with us when we're making product applications that we're focused on those targeted nutrients. Also from a chemistry standpoint, right? This is Mulder's chart. If you haven't seen it, this is one that keeps me awake at night a lot of cases as I'm building programs. I'll build out what I feel is most agronomically viable for that particular site, and then I'll spend a good deal of time staring at this chart and understanding what are those chemical relationships between the mineral nutrients, not only the targeted ones that we mentioned, but also those baggage elements, and how is that going to impact the nature of my specific system or my specific soil type. And so we see in red here, those are the antagonistic relationships between different mineral nutrients, and then green are the synergistic relationships. So now that we have a rough idea of some of the decision-making processes to go through in terms of building out a program appropriately, and we start to look at individual inputs that are available to us as a grower, as an advisor, it's really important that we ask some critical questions when deciding on executing a particular program. Starting with generally speaking, how does this product help support our agronomic objectives? Because your objectives may be different than the guy next door or gal next door or somebody else down the road. And so you need to be clear about what your objectives are and what your targets are as a grower or an advisor, and how does this product fit that need. Understanding what is the total nutrient load per unit of measure, both in liquid form or dry form. This is going to have implications on how much of that particular product do you need to be able to supply the nutritional needs of that crop for that particular stage or that particular season. In addition, you also want to be cognizant of what is the total nutrient load per dollar, right? And this is something that it blinds people in a lot of cases, and they just look at what is the target nutrient that I'm focused on? What is that price per unit of N? What is that price per unit of K? But in a lot of cases, in the form of sulfate, if it's applied in a time of season where it can be utilized, or in the case of like a calcium nitrate or something of that nature, there's additional value in those other mineral nutrients as long as you're figuring that into your program. And so there's a need to look at the total nutrient value, and then also, most critically, what is the expected ROI that I'm going to get from making this application? Not what is that first upfront dollar figure, but what is the return on that investment that I'm going to get at the end of the season, and the level of confidence. Additionally, there's handling and safety concerns with every product, particularly more concerns, I think, with liquid products in a lot of cases. Tank storage, the safety of those tanks themselves. There's considerations in terms of like salt out temperatures that particular products may actually salt out at temperatures that are typical of overwintering here. And that bleeds into storage considerations. But ultimately, the last one that we need to think about from a site-specific manner is also, does this application strategy for this particular product match what my capabilities are as a grower? Do I have the infrastructure to be able to deliver this product in the right way that's going to maximize the efficiency of that particular product? So got some overlap here in the graph and the labels, but here I just highlighted a few of the most commonly available nitrogen fertilizer sources. And so urea is not one that we typically see a lot of utility in commercial almond production. We did want to just highlight some of the commonly available ones. We have dry products in the solid bars, and we have some of our liquid products in the striped bars. And the point of this graph is just to highlight what are some of those options that are available to us from a synthetic standpoint. What is the analysis and the nutrient load of that target nutrient that's coming along with those different products? And then what is that additional nutrient load that we should be aware of, whether it has an antagonistic or synergistic value for us in our system? As Katherine mentioned, looking at the relatively quote-unquote free nitrogen that comes along in our systems, this is really important also. And so the table that the ABC Nitrogen Best Management Practices pamphlet put in there is really useful. But I want to take it one step further, and when we think about what is the nitrogen content or the nitrogen concentration of our water, it's not only thinking about how do we budget that into our total program. If you're getting 40 pounds of nitrogen coming in with your water at 4 acre-feet, but it's where does that water get applied in the program as well? Because if you are putting that budgeted 40 units of nitrogen in at the beginning of the season between 70% leaf out and nut fill, you've essentially starved that tree during that period of time because you're not going to be applying the bulk of those water resources during that period. Those are going to be showing up more so in that later third of what your demand curve is. And so you need to be cognizant of where you apply that 40 units in that season program. And then some additional considerations for nutrient forms of N, and here I kind of broke these different sources into their urea and ammoniacal nitrogen balance versus their nitrate balance. You see CN9, which is 100% nitrate on the far right side, versus urea, which is 100% urea on the left-hand side. The reason for that is that urea transforms quickly over to ammoniacal nitrogen in most cases, and so we really are just comparing ammoniacal to nitrate, but there is some critical impacts that nitrogen products have and their forms have on our pH, and so we'll take a look at that in a little bit. But urea and ammoniacal typically are more acidifying agents versus nitrate being more of a basic or neutralizing in some cases agent. As Katherine showed in some of the old IPNI graphs from 2018, I believe, that urea can move nearly as quickly as nitrate because it is an uncharged molecule, and so that's really important for us to understand as we're fertigating these products, that we're not moving that urea moving that urea as fast as we would move nitrate in that particular situation or close to it. On the other hand, ammoniacal nitrogen, being a positively charged ion or compound, that's going to be bound up on our organic matter sites, those negative charges, as it undergoes nitrification and becomes plant available over time. And so these balances of urea and ammoniacal nitrogen versus nitrate nitrogen are really important when we start to look at demand versus timing of application and some of our soil-specific conditions. So here's one that I wanted to look at, and I've seen in many references, ammoniacal nitrogen being converted over to nitrate nitrogen in days to weeks. Here I wanted to highlight from the IPNI graphs from 2018, some soil conditions from Modesto specifically, because it's probably the most relevant and it's where my research farm exists, so it's most relevant to me. But if we look at this Modesto region, and we look at this period of time where we are typically and historically applying nitrogen fertilizers. That's between 70% leaf out and June 1st, which is an outdated practice to cut off by June 1st, in my opinion, but that's a whole nother debate as we discuss continuous fertigation. But needless to say, this is our traditional window of applying nitrogen fertilizer. And so if we look at the temperature ranges on the lower and upper bounds here, from this particular graph, we see that we're in the low 50s at the beginning of the season, and we're in the upper 60s maybe by the end of the season. And that's where we're typically applying that fertilizer. There's not a line there for mineralization rates on the right-hand graph for upper 60s threshold, but if we throw it somewhere there between 50 and 75, we can see that the 65 range here would dictate that our nitrification rates during the period of time where we're actually fertilizing could last anywhere between 5 to 12 weeks. And that's essentially, again, based off of what these curves are and our hypothetical 65-degree threshold that we've identified there. So something to be cognizant of, but soil temperatures really do play a critical role in the rate of availability of different nitrogen fertilizers. Looking from a chemical standpoint, in most cases, we will likely exist in the almond growing regions in the pH range of 6 to 8, we'll say, more likely probably 6 to 7.5 or so. But this is important also in terms of nitrogen source. And so pH below 7 on the acidic side of this pH scale is in most cases going to favor fungal communities. And so this is important because the bacteria colonies that are required to be able to transform urea and ammoniacal sources into plant available nitrogen are going to be more favored on the upper end of that pH scale. And so on the acidic side, this may be an area that may be more favorable to nitrate-based fertilizers, whereas that upper side of 7 may be more favorable to urea and ammoniacal-based sources. And both of those on those far ends are going to try to work that pH back to neutral by their activity and their chemical nature. Some additional considerations in terms of fate of nitrogen sources, and considerations in our particular farming operations is that low soil temperatures can really challenge microbial conversions also of those urea and ammoniacal sources. Low soil temperatures, that biology is moving slow, they're not actively going to be making that conversion over for us. Saturated soils also, there's challenges there in that we can actually have more ammonium volatilization, and so that's NH4, and also if there's a high presence of nitrate under saturated conditions, we can actually have denitrification of that nitrate fertilizer and lose that to the atmosphere as well. I mentioned the pH scale in terms of urea and ammoniacal on the upper end, but one challenge is that when we do get above 8 on the pH scale, which is not very common, I would say, in the almond growing regions, that we will see additional volatilization of ammonia taking place from urea applications. And again, just reiterating that urea and nitrate from an environmental fate standpoint can leach nearly as much as the other. Here's a study that I found particularly interesting, and this was similar to kind of work that we've been doing at our research farm for a number of years, but looking at comparing standard UAN-based applications, which in this particular case was 4 applications through the growing season, and that is in the blue bars here, and then comparing that against a high-frequency UAN-based strategy in green, and then a high-frequency nitrate-based strategy in red. Now, nitrates usually get a pretty bad rap in terms of their leachability. They are very leachable, but when managed appropriately, this work is really showing that there was actually a lower concentration of nitrate in deeper depths of the soil solution in days 1, 2, and 3. That is moving from left to right, days 1, 2, and 3 after these applications took place. These applications took place in midsummer, so high temperatures, so a pretty rapid conversion of urea to nitrate in a lot of cases. But what we see on this far right side is that urea ended up 14 times higher with nitrate values, or I'm sorry, the UAN had 14 times higher nitrate values at this lower depth of 60 centimeters than the corresponding high-frequency, low-volume nitrate-based applications. And so this is really critical because when we think about UAN, you're looking at 50% that exists as urea, which can move through that profile, and then you have 25% each of ammoniacal and nitrate. So that nitrate already made it down in 3 days, 14 times higher than the high-frequency nitrate program on the UAN side. But also that urea is not going to be far behind that. So once that urea lands, it's going to convert over to ammoniacal, bind to that soil, and then convert to nitrate over time. But we're going to be continually putting water on top of that in that process and potentially leaching that new converted nitrate below that root zone as well. So something to be aware of. We'll switch over to potassium, and similar to Katherine's presentation, potassium is a much smaller component of this presentation because there's just not as much in terms of environmental fates and things of that nature and regulatory pressures around potassium. So here we look at some of our common dry products in the solid bars again, and our liquid products in the striped bars. Not a whole lot of options, I would say, in terms of liquid products available to us. We do here, again, show a comparison between the different forms, either dry or liquid. Also, the nutrient load that is coming with that target nutrient that we're looking for, that K2O or potassium. And then some of the additional components that, again, are coming along with that product in terms of additional nutrient compounds. So an alternative source of looking for potassium is also looking at compost. There's a lot of interest in that these days, I'd say, kind of garnered around the Healthy Soils program and some incentive opportunities. The two typical sources that we would see would be green waste or manure-based composts. And even within manure, there are different animal species, dairy versus poultry, that may exist that have different nutrient loads. It's really critical that when evaluating the opportunity costs for the different nutrients or the different manure sources or green waste sources of compost, that we're looking at this on a dry weight basis. And so I know in the past I've gotten analysis forms from different producers that provide me a wet base analysis, and that's not going to be effective in calculating out the total nutrient value that you're going to get from that product. So that's really critical. In a lot of cases, we may not see compost as being a really predominantly nitrogen-based source because some of that nitrogen gets volatilized off in the open composting process, and a lot of it's going to be tied up on that organic matter similar to phosphorus. And so both of those two elements may take multiple years from a compost application to be fully available to that crop. But potassium, on the other hand, that's going to exist in the elemental form in that potassium or in that compost product. And so that's going to be fairly more available in that first year. And one thing to note that in just a simple calculation based off of a Recology label that I had from years ago, green waste product, is that if I was looking at supplying all of my potassium needs from a green waste product with that particular analysis that I had, that I'd be looking at about 13 tons of compost per year per acre to be able to supply the total potassium needs. And so it's not something that we necessarily probably want to think of as our sole source, but something that can be utilized to amend some of our additional synthetic applications. Some last considerations in terms of nutrient form for potassium. High soils, I believe it was mentioned previously about cation balance or basic cation balance, and there's competition between basic cations, and those basic cations being calcium, potassium, magnesium, and sodium. So if we have a high soil pH and we have a high level of basic cations, calcium, magnesium, sodium, we're going to have competition with potassium, and it may not be as readily available. In that particular situation, the thiosulfate in KTS will actually acidify that soil environment, and so that may be a better application for the higher pH soils. Potassium itself actually is taken up differently than nitrogen. Nitrogen, in a lot of cases, although there's some regulation in terms of plant demand, basically mass flow that helps move nitrogen into the plant. Whereas on the potassium side, you do have active ion uptake channels that are required. And so this is important when we think about the placement of our potassium sources and making sure that we're hitting on our broadcast applications on the dry side or on our fertigated applications that we're getting that product into the active root zone within that herbicide strip so that the roots are able to have readily available access to that product. Just as a word of caution, I always am very careful about rates in terms of KTS if we're looking at temperatures that are over 90 degrees Fahrenheit. I think if anybody's seen burn at any point in time, that gets stuck in your head. Not to say that it can't be used, but just be cautious of the rates that are used. Similarly, from a burn standpoint, looking at MOP, and that's something that I recognize the challenges economically in the industry, and that MOP can usually be a more economically viable form of potassium, but be very cautious, as previously noted. Almond trees are very sensitive to salt, and so make sure that we're utilizing that chloride at least at times of the season where the plants are not active, maybe on those peripheries, and making sure that we can hopefully leach all that chloride out of that root zone before those plants become active again. I did mention previously about potassium salt out, and so when we look at some of our liquid products, this is going to be specific to liquid products. Our potassium acetates and our potassium thiosulfates, they have fairly low salt out temperatures, and so we can be pretty confident in carrying those over winter in a tank on site. Potassium nitrate, on the other hand, has a fairly high salt out temperature, not something that you're going to want to keep in tank over season, and likely something that you maybe want to focus on a little bit later season applications. But you can actually put, it usually comes in the form of like a 3-0-10 in a liquid product. You can actually dilute that to a 2-7-0-9 and gain about 20 degrees on the salt out temperature. And lastly, it was addressed a little bit about K fixation, and that can be a really critical thing to be cognizant of, specifically in terms of where your farm site is. And so we have lost our last graph or our last chart. That was actually two shots of kind of the upper San Joaquin Valley into the Stockton, Lodi, Clements area maybe, that was historically wine grape growing region, that there are a lot of notably potassium fixing soils in those regions, as well as a map that I saw that was through the lower part of the Central Valley, lower San Joaquin Valley, Kings, Tulare, Fresno County, that was historically cotton growing ground, that they had also mapped out some K-fixing soils in those regions. So if you are in K-fixing soils, I'm sure you likely know where you are already, and it's important that you look at that continuous fertigation type of strategy to feed only on demand and not think that you're ever gonna get to a situation where you're gonna be bulking up that soil and loading up those potassium resources in a K-fixing soil. And that's it.
Thank you, Devin. Nice. We have a few minutes for questions, so raise your hand if you have a question, please.
Hey, good morning. Thank you for the detailed information.
Absolutely.
You know, something we've been struggling with, I know they call it the good farmer disease, but when you've killed off most of your good growth and fruiting spurs, it doesn't feel like it. Talking about whole rot.
Yep.
In the previous presentation, as well as yours, we're talking about how long it takes the nitrification process. You know, they tell us to cut off nitrogen fertilizers in about mid-May.
Yeah.
But it sounds like we could still be getting significant sources of nitrogen 5 weeks after our last application.
Yeah, and it obviously depends on the source and the balance that you've been using throughout the course of the growing season. What I would say to the whole rot issue specifically is, again, pushing for the continuous fertigation strategy. We've been executing this at a research farm that I manage in Modesto for 4 years now. We just finished our 4th growing season. And what we've seen there, I'm not going to by any means say that this is proven, but what we have documented over there for the last 4 years is a 33% reduction in whole rot using a continuous fertigation strategy with equal nitrogen rates to other slug-based strategies. And so I've had this discussion with Dr. Brown in the past, and my interpretation is that early season excessive nitrogen rates will actually predispose those cell walls and weaken those cell walls in some of those whole cells and predispose them to fungal infection later on down the road. And so no matter when you cut off, if you've already created that damage early in the season, you've already done the damage, and you're not going to be able to save yourself dig yourself out of that hole.
Got it. Do you have a recommendation on what material to start using, say, the later months? Or more just continuous?
I think that, you know, in a lot of cases, we'll see a lot of more ammoniacal and nitrate-based products being utilized early in the season. And the anecdotal evidence is that growers see their trees green up faster. And a lot of that due to soil temperatures, I think. But I think by the time you get to mid to late season, any product is going to transform well enough to be able to get your needs met and not hopefully string you out too far in that release curve. And making sure, again, but just really working towards that continuous fertigation strategy so that we're only supplying the rates that are needed at the particular time.
Got it. Thank you very much.
Absolutely.
How's it going, Devin?
Hey.
Hey, so in regards to the Mulder chart and nitrogen and potassium not being synergistic,
Go back to that.
Is there some uptake need that you might get more benefit out of putting them both in at the same time? You know, at that point in the season, since we are going at a specified rate for nitrogen and potassium, to maybe get some more efficiency?
So the synergy between nitrogen and potassium applied at the same time. I wouldn't be an expert in this space, but what I would suspect is that, you know, potassium is very strong mineral nutrient in terms of influencing the transpirational stream. And so if we are providing a better transpirational stream through the use of potassium, that we're going to get better uptake and carry in of that nitrogen, along with some other nutrients potentially, and keeping that, you know, that root zone actively exchanging nutrients based on demand. They're not synergistic themselves, no. But executing our programs based on demand, I think, is always going to be a positive relationship.